Hello again, Calc 2 students. We are past Taylor series. I told you guys that integration with trig sub was the hardest thing in the class. Taylor series is probably the second. We are now in the home stretch. We're going back to the third concept in class, which is that integration is actually useful. So we're going back to chapter 8, and we are going to talk about area, and that's going to lead us to volume and some other coordinate systems. Alright, so this first part of our three-city tour, as it says there, we're in Areaville. This is, hopefully the beginning of this is something you learned in Calc 1, but we're going to spread it out a little bit and change things and kind of use it as an intro as we head to volume. So this curve up here is the integrand given there. That's a graph, and then there's the little slice for adding up a sum to do an integral, right? An integral is really an infinite sum of rectangles. And so these parts here ask about what means what. So which part of the notation above means that we're summing? That's the integral sign. And we're adding all these rectangles. Which part is the height? That's the y value, so that's this thing, right? The curve is y equals that. So that's the height. The width of the rectangles, remember the rectangles are getting infinitely thin. That's the dx. And then the 0 to 12 are the start-stop points, I guess is what I'll call them. So we're only integrating this stuff. We're going to begin at x equals 0 and into x equals 12, and that's the area that we want. They want me to determine the area. I'm going to go ahead and do this by hand, even though we've all done our integral gateway, because I want to make the point. So I'm going to do this with a w sub of what's inside the root. dw, first write it maybe like this. And then you'll see that dw is really minus 1/3 dx. And so I'll have a minus 3 up front. I'll change my limits to 4 and 0. So they're upside down. That's okay. And I have w to the 1/2 dw. Let me go ahead and keep writing across the bottom here. Flip it here, 0 to 4. And then do the integral. Use the power rule. So it'll be 2/3 times 3, which will be a 2. W to the 3/2. 0, 4. The 0 won't matter, and I get 2 times 4 to the 3/2, which is going to be 16, I believe. You can check me on that. Okay, so we were able to do that integral, but it was kind of annoying. We had to use an integration technique. We had to use W substitution. We're going to do the exact same integral a different way. Maybe you did this in Calc 1, maybe you didn't. I'm going to draw a sideways rectangle. And I'm going to add these up vertically rather than horizontally. So I'm going to stack rectangles. To do that, if this was dx over here, we're going to call this dy, and so then we're going to call this an x distance, right? So we need to solve this for x. So that would be y squared equals 4 minus the third x, based on what I did before. 1/3 x equals 4 minus y squared multiplied by 3. And you get this deal here. Using the same kind of reasoning and the stuff I wrote up there, this is the x value. This is dy. Now my limits of integration are y values, and if you look closely, it's kind of hard to see the scale, but this is going from 0 to 2 because these are y values, 0 to 2. Still the same shaded region. Okay, evaluate this integral. Now I only have to do the power rule. This is 12y minus 3y cubed over 3, which cancels. Plug in 0 and 2. The 0 doesn't matter for this problem. And you get 24 minus 8, which is 16. Hey, we got the same answer both ways. And the dy integral was easier. So that's the point, is that you can do integrals sideways when it's helpful. It's not always helpful. Sometimes dx is better. But that is an important idea. And we're going to use it again on the next page. Okay, so page 47 in the workbook here. I've got two areas here I want. The eye of Sauron here, and then kind of this boomerang looking picture. So the first one I'm going to do with dx, and you'll see why here in a minute. Really, when you think about these rectangles, that is a dx integral. That makes sense. This kind of integral, you'd be subtracting the curve from itself if you did that, and that's not helpful, so we don't want to do that kind of rectangle. Okay, and so notice these rectangles are the top function taking away the bottom, because this would be the whole rectangle of the top curve, and then this would be the one at the bottom curve, right? And we're gonna just take the difference to get the space in between. Okay, well, first off, where do these graphs intersect? You can plot and click some buttons, or you can look up here, or you can solve this algebraically, but you should get -2 and 2. Okay, so those are the endpoints of where I care about. And then I want an area between the curves. So I already talked about the dx rectangles. Okay, so I want to take the top curve minus the bottom one for a dx integral. The top curve is the frowning parabola, which is this, and then the smiley parabola is the bottom one. And then remember that I always say to simplify if it's convenient. So right now I would rather simplify. The limits of integration, we found those points of intersection. So 24 minus 6x squared. I simplified that, and now I do the integral. 6x cubed over 3, which becomes 2. Plug these in. You're going to get 48 minus 16. And then I think you're going to get the same number again. You're going to get minus 48 plus 16. So altogether you're going to get, I think, 64. You guys have to check my math there. Even if my arithmetic is off, you get the principle of the problem. All right, so we had to do a dx. I shouldn't say we had to, but it would have been a terrible idea to do a dy integral here. It's the same principle here. Dx looks fine until you get to here. Now you're taking the same curve minus itself, and that's complicated and annoying. You'd have to make two integrals and split it here. Instead, if you do, so don't do that, do a dy integral, then it's always the right curve minus the left curve. So think of more negative minus left negative. So top minus bottom on this side. On the right side, it's going to be right minus left for a dy integral. Okay, so this curve is y equals x. If or x equals y, I should say, solve for x. I need to solve this one for x as well. So this is 12 minus y squared all over 4. Or you could put 3 minus 1/4 y squared. That'll be easier to integrate. Okay, where do they intersect? So this point and this point. You can use a computer. You can set these equal to each other. I think they intersect. I can't see that very well, to be honest. I think at minus 6 and 2, but let's check it. So let's just do it by hand. So this would be when the x values are equal or when the y values are equal. Notice that y is always equal to x, so all I need to do is plug it in. This other curve, just make x and y the same. It doesn't really matter the variable. And then solve this equation. So y squared plus 4y minus 12 equals 0. Factor it, and I think you get y plus 6, y minus 2. So y would be 2 and y would be minus 6, which is what I thought they were, so that's good. And then because y is equal to x, this point is minus 6 minus 6. This point is 2, 2. All I really need is the y values, though, minus 6 and 2 for the integral. Okay, I already drew the Riemann sums. I already talked to you about how we want to do it horizontally, which makes it a dy. So that means we're going to do dy here, and then for the length, we want to take the rightmost curve, which is the parabolic one. So 3 minus 1/4 y squared, and then minus y is the line. Alright, so we're going to go from minus 6 to 2. 3 minus y squared over 4 minus y dy. Evaluate the integral, so 3y minus y cubed over 12 minus y squared over 2, plug in minus 6 and 2. That's going to be a little bit of annoying to work out, but you should get, drum roll, 21 1/3 when you're done. Alright, so the first page we saw that dy can be convenient. Here we see it's practically necessary sometimes. So this little sheet is just about when to use dx, when to use dy. Okay, we got a Plickers problem to wrap this up with, and we're going to do several Plickers problems that are going to lead to the same idea about kind of broadly doing these difference integrals. So I have two functions given in the first graph, and then so c of x is the cubic, L of x is the line. So we mark that c of x is here, L of x is here, the line. Which of the following graphs represents this as area as a function of x? So basically what I mean is that the graph I'm looking for has this much area as its y value, and then this much area as its y value, and then this much area as its y value. So I'm recording at each y how much area I have so far. So which graph is that? Don't worry about too much about this expression, but which graph represents the area between them, where it's always the curve minus the line. Well, the real question first, when you look at these four graphs, is whether the curve should go up and then come down, or whether it should stay the same. The integral that I scribbled out had the curve as the top one, the cubic, and then the line as the bottom one, but they flip halfway through. That means the integral is going to change sign, and I really should get a graph that comes back down to 0. All this area together, because this is going to be negative, according to that expression, is going to end up being 0. So not this one, not this one. And without that stipulation, it could have been one of those, but we're going to say that we have that stipulation, so we want it to come back down to 0. The area is going to switch for a second, not for a long time. This implies that there's a long time where the areas are where there's no change, right? We don't have that, so it's not this one, it is A. Alright, so that's the beginning of 8.1. The next video we will do 8.1 more broadly, thinking about slicing.